Welcome back, everybody. In our next section, we're going to be looking at profile number 1 for multicast routing over the layer 3 VPN. And before we get to this, there was a question from the last section, was can I do profile 0 without doing the BGP signaling in the core? And the answer is no, because that's effectively how the endpoints learn where they are and then figure out how to form the tunnels to each other. Now we'll see this is going to be different from profile number 1, where we're going to be using MPLS as the transport as opposed to a GRE tunnel. And we're going to simply specify where we want the middle of the tree to be built, and then all of the PEs are going to build the tree towards that device in the core. So in profile 1 specifically, we're going to be using multi-point LDP in order to do the underlay signaling. So this means that in the service provider for this design, you do not need to run a PIM towards the core. You do still need to run PIM on the PEs towards the CEs, and then the join messages would be sent towards the core of the MLDP tunnel and then be distributed back out to the other provider edges. The overlay signaling is still going to remain as PIM. So again, this is why you need to run PIM on the customer edge to provider edge link. Okay, nothing is going to get you away from that. The difference likewise here for profile number 1 versus 0 is that the encapsulation is MPLS. So next, before we get into the command line, let's look at the config examples that Cisco has. So again, these two documents are configuring MVPN profiles within iOS and then the MVPN profiles within iOS XR. So for iOS, in this case, we're doing profile number 1. It says under the VRF, we need to specify the VPN identifier. This value here is what needs to match between all of the PEs that want to participate in the multicast VPN routing for that particular customer. Now, since we're not using BGP auto discovery here, you need to make sure this number is matching because this is where effectively the auto discovery is happening instead. Okay, the second portion is we specify a default MPLS MLDP neighbor, and this is where we're building the root of the tree. So in our example here, we're going to use router 2 as the root of the tree. So this means that there would be a label that would be bound going from router 1 over to router 2. Okay, so we have a label. And then likewise, there's going to be one from XR1 to router 2, from XR3 to router 2, from router 3 to router 2. So we're now going to receive a PIM message in from the customer. We send it to the root. The root is then going to replicate it down to all of the other members of the multicast VPN. Okay, so we need to make sure that whatever value this is, that it's reachable, that it's a node running MPLS in the core, and then everybody has to agree on it. Okay, so that's pretty much it. There's only 2 commands that correspond with profile number 1. Okay, under iOS XR, a little bit more involved. So we specified the VPN identifier. Okay, again, has to be the same one as we're doing on the other side, but note here that it's a different value that they're using for regular iOS versus XR. So if you're just copying and pasting the documentation, be very careful as usual. You do have to edit these values, make sure they match between the different endpoints. Okay, then under PIM, we're specifying the RPF topology. RPF for 1 being just whatever their VRF name is that they're using. So I copied and pasted this particular command, but our VRF is not named that as VRF B as in Brian. It could be any policy name, it's just a string. The key though is that under that route policy, we're setting the core tree to be multi-point LDP. Now, I'm not 100% sure if they actually show, yes they do here, which is MPLS LDP and then MLDP. So we need to specify this on XR to turn the process on. And I don't believe there's anything in regular iOS we actually need to do. Let's look at the show run, pipe include, LDP. Now, in the case of regular iOS, it's just on by default. When we look at the show MPLS LDP neighbors, okay, once the neighbors are formed, and then if we look at the MPLS neighbor, LDP neighbor detail, This should tell us if the capabilities include point to multipoint and multipoint to multipoint. So these are the two that allow you to do the MVPN, the multicast VPN, or the MPLS, or the VPN over MPLS layer 3 VPNs. So in other words, this is just a code version issue. As long as you have the code in regular iOS that supports MLDP, as soon as you turn LDP on globally, then MLDP is also going to be running. Okay, so next, under XR, we were specifying the default root of the tree. Okay, we're going to be specifying this as router 2. Okay, so let's look at the config from the regular iOS boxes. So this is going to be on router 1 and router 3 are the regular iOS or the iOS XE PEs. And let's see, what were the steps specifically? So we go under the VRF, specify the VPN ID, and then under the address family, specify where the root of the tree is going to be. So on router 1, let's look at the show run VRF. Show run VRF. VPN ID is simply 1:1, and it says the default MPLS MLDP root is going to be router 2. What this now means is that when we look at the show MPLS forwarding table, we should have an MDT that has a label bound to it. Okay, same thing should be true on router 3. When we look at the show MPLS forwarding table, we should have the multicast distribution tree for VPN 1:1. Okay, under XR, under the VRF, we have the VPN ID. So if we show run VRF, VRFB as in Brian is VPN ID 1:1. Show run router PIM. Okay, we have our RPF topology called RPF for 1. If we show RPL, this is using the MLDP default tree. Okay, it basically means that there's just one tree for all traffic. So everything is going to be sent to router 2, and then from router 2, it's distributed. You can almost think about this like router 2 being the rendezvous point, but the difference is that router 2 is always going to be in the data plane here. So more similar to bidirectional PIM, for example, where you forward the traffic up to the RP, then the RP sends it down the shared tree to everybody else. Same exact type of logic when we're using the default MLDP feature. Okay, so before we before we send packets, let's go ahead and do a packet capture. So let's go over to router 2, okay, who's the core of the tree. And we're going to go to interfaces to router 2. Okay, router 2 gig 2, traffic capture. Create. Okay, and now let's look at this on the customer side. So if the customer network is working, we should be able to go to, let's say, router 4 and look at the show IP PIM RP mapping. And ideally, we should see router 5, who is the bootstrap router. So the bootstrap router messages are going to go from 5 to 1, 1 over to 2, 2 back to XR1, and then to router 4. So on router 4, let's show IP PIM RP mapping. Okay, we do know about the rendezvous point. Okay, so that's good. Let's try now joining a group from router 8. So on the loopback, let's say IP IGMP join 224.11.22.33. Then on router 5, who is the rendezvous point, let's see, does it know this in the control plane? Show IP mroute for that group. Yes, it does. It says when packets come in, I don't know where they're coming from because the sender hasn't been registered to me, but I know about the receiver. The receiver is located on gig 2.15. Okay, so this is the correct procedure. We signal from the customer network, it goes to the other customer network. This must mean in the middle that everything is working. Okay, so router 8 is now joined this particular group. Okay, let's go to router 7 and let's ping that group. Okay, so ping that address, high repeat count. And now let's go ahead and do our capture from router 2. Actually, the capture is already running, so let's go to download the capture. And let's look for ICMP. Okay, so we see the packet coming in link 37. Okay, 37 is the link between router 7 and router 3. So it's coming in as just a native IP packet. Okay, next it's going out 23. So we see that it is a PIM tunnel because we're trying to register the message. Okay, notice that this is a unicast. Unicast it has two labels because we're doing regular VPN switching towards 5555. Okay, so what we need to look at is what happened after the register was successful. Okay, here now we see packets coming from router 7 going to that particular group, but now it's encapsulated inside of MPLS. So let's look at from router 2's point of view, what happens when label number 22 comes in. So on router 2, show MPLS forwarding table. It says 22 comes in and we need to replicate it across the multicast distribution tree. So it's really going to go out multiple interfaces. It's going out 211, it's going out 213. Okay, it's not going to go back out the same interface that it came in, but it's going to be replicated down to these two. So we can see that from router 2's point of view, it has a bunch of labels that are associated with the multicast distribution tree because it is the root of the tree. And the way that we're making it the root of the tree is simply by statically specifying that under the VRF. Now, as you could probably guess, from a design point of view, there is a problem with this where you're only specifying that one node is the root for the tree. So if router 2 goes down, then we won't be able to forward multicast traffic. So there's two ways in general that you could fix this problem. Okay, talking about redundancy here in the network. One option would just be to specify multiple routes. So we say that router 2 is the root, and that we specify that, let's say 12, 12, 12, 12. And show run, do show run VRF. Now it lists both of them. So in this case, we would be replicating the traffic both ways between the different routes of the tree. It's not going to be optimal in terms of the data plane, but the advantage is that if one of them goes down, the other one immediately picks up the traffic. You don't need to worry about any convergence. A second way to deal with this would be to use Anycast. So let's say, for example, that we want router 2 to be the root, and we want XR2 to be the root. One way to do this would just be to specify both of their addresses, 2222, 12, 12, 12, 12. Okay, so on each of the PEs, we specify both. So this means that from router 1's point of view, when a multicast packet comes in, it goes to both routes, and then they replicate the traffic down to the other PEs. So it is going to be inefficient because we have multiple replications. And then once it goes to the PE, they're going to be sending just one of the feeds down to the customer. Okay, an alternative to this would be to use Anycast logic. So let's say that router 1 specifies the route as 1, 2, 3, 4. On XR2, we create a loopback 1, 2, 3, 4 /32. On router 2, we create the same loopback 1, 2, 3, 4 /32 and advertise them into IGP. So router 1 simply based on the fact that, well, actually, this is kind of a bad example because they're directly connected in both ways, but it's going to choose one of them based on some sort of hashing mechanism. And let's say that the join message goes towards router 2, saying add me to the tree for the labels. Then router 2 goes down. Router 1 would realize that, hey, I lost reachability to that device based on the unicast routing table reconverging, and it would trigger a change to rebuild the tree in this direction. So with the anycast solution, when one of the routes goes down, you would have to rebuild the tree. If you specify just multiple routes, they would both be active at the same time, forwarding traffic. Then if one of them goes down, you just immediately switch over to the other one based on your tuning of the IGP. Okay, so our final result then is from the customer router that was doing the pings. And let's see, did we look at the ICMPs? We look for GRE, ICMP. All right, let's do a new capture here. So we're going to capture on router 1. Well, actually, no. We'll capture on 2 because 2 is the root again. Okay, so 2 is currently capturing, and then let's go ahead and do the ping again. So we're pinging to router 8. Okay, or actually to this multicast group that router 8 is joined to. And then our traffic capture from router 2. Okay, there's a question here. If you have 2 routes, do they sync their M routes so they can take over for the active stream? What's kind of interesting here is that the devices in the core, they don't have the M routes. So in this solution with Profile 1, you could completely turn off PIM in the core. The only thing that they're doing is label switching. So if the label is pre-built, then they're able to forward. If the node crashes and the labels aren't rebound to a different route, then you won't be able to send any multicast traffic. Okay, so in our ICMP messages, we should see that these are now label encapsulated. Okay, not for the register message, for the regular pings. So we should see like this. Okay, so this is on port 12, which is between router 2 and 1. We're using label number 25. Okay, so let's go to router 1 and look at what label 25 is. Show MPLS forwarding table. Label 25 means it came in from the MDT tunnel. Okay, if we look at the show IP M route for the VRF, the edge still needs to run regular PIM. Okay, reason why is that the overlay signaling is still going to be PIM. So this is the customer to the provider. We're still using PIM, but the underlay is signaled with multi-point LDP. So on the edge, if we look at, so let's go back to the diagram. On the edge, if we look at the show IP PIM VRFB neighbors, we're still forming PIM relationships across that tunnel. The difference here, though, is that it's not a GRE tunnel, it's an LSP virtual interface, meaning it's using labels in order to reach router 3, 11, and 13. So what multi-point LDP is allowing us to do is to take one label in and then replicate that packet out with multiple different labels. Okay, and we saw the other change here was that the encapsulation is MPLS. It's not using GRE. It's using MPLS forwarding. Note again that in this solution, we do not need BGP to do any type of signaling or auto discovery because we are statically defining where the traffic is going to go from a labeling point of view in the core. We were doing that by specifying the MLDP route.